Hello friends, we are bigdatahandson.com. Today is day 28. We are going to see other two dimensionality reduction algorithms that are linear discriminant analysis LDA and the kernel PCA advanced version of the principal component analysis. So we'll see these two algorithms today, and we have seen the other algorithms like principal component analysis and a priori eclat mean shift. These are the clustering algorithm, we know that, right? And we have seen support vector, naive bayes, random for addition tree. So from 15 we have started machine learning, and now we are going to be complete the machine learning algorithms. From tomorrow we'll complete the machine learning. So today is day 28, and tomorrow day 29 will complete machine learning, and then we'll start deep learning from day 30. Okay, so all the previous videos from day 1 to day 27 you can find it in our YouTube channel bigdatahandson.com. So this is our YouTube channel. You can find the videos uploaded here. So if you subscribe to our channel you will get all the updates. So, and this is our website bigdatahandson.com. Okay, you can visit our website. So this is our contact number. If you have any doubts you can send messages in this number, and this is our email address. You can send email through this email address. Okay, so now we'll continue with our class. So today's topic is linear discriminant analysis. So this linear discriminant analysis is a dimensionality reduction algorithm. Okay, it's most commonly used as a dimensionality reduction technique in the pre-processing step. So all the dimensionality reduction algorithms we apply before the model creation, right? So that's why it's a pre-processing step. Okay, and step for pattern classification. Sorry. So where we are. So it's a pre-processing step for pattern classification and machine learning application. So we'll see about what is pattern classification, and one more thing, in linear discriminant analysis we mostly apply for classification problems actually. So I will tell you why we are applying for classification. And the goal is to project a data set onto a lower dimensional space with good class separability. So in linear discriminant we try to separate the classes, okay, on a lower dimensional space, okay, in order to avoid overfitting. So that's the reason we are applying the linear discriminant analysis, and also reduce the computational cost. Okay, so why we are saying class separability and pattern classification is because we have a difference between the principal component. The yesterday we have seen principal component analysis and the linear discriminant. So these both are same because the common thing in the principal component analysis and linear discriminant analysis is they are the technique is common. So it's same as the PCA, the linear transformation. The LD and PCA both does the linear transformation, but the main difference is PCA is unsupervised, LDA, the linear discriminant, is supervised. Why we are seeing PCA unsupervised is because in the PCA principal component analysis we doesn't care about the target variable, right? We ignore the target class labels, or you can say class variable. We ignore the class labels. Okay, and its goal is to find the directions, right? In PCA what we do, we find the directions. That's the direction minimizes the variance in the data set. That's the goal of the principal component analysis. But in the LDA, what we do is, it's in LDA is a supervised learning algorithm. Why? Because it computes the direction, but that will represent the access that maximize the separation between multiple classes. Okay, so we consider the class here, but we don't consider the class labels in the PCA, but we consider the class in the LDA. Okay, so that's the main difference of principal and linear analysis. So you can see here in the image. So the PCA components access that maximizes the variance, and LDA maximizing the component access for class separation. Okay, so this is the difference between principal component analysis and linear discriminant analysis. So the steps involved in the LDA. So we have 5 steps. So first step is compute the d-dimensional mean vectors for the different classes from the data sets. Okay, and compute the scatter matrices in between class and within class, and compute eigenvectors and eigenvalues, and sort the eigenvectors by decreasing eigenvalues, and we're going to choose the k eigenvectors with the largest eigenvalues, with values larger eigenvalues from a deep cross k dimensional matrix. So that's our WW matrix here. And then in the fifth step, what we do is we use the D cross K eigenvector matrix to transform the samples onto a new subspace. So this can be summarized by the matrix multiplication. So yy equal to xx cross ww. Okay, where xx is the nd dimensional matrix representing the n number of samples, and yy are the transformed n cross k dimensional samples in new subspace. Okay, so and that's it for linear discriminant analysis. Let's see the implementation here. So now we'll create a new file and save this file. We'll save as lda.py. So now what I'm going to do is I'm going to show the difference between the linear discriminant and PCA and principal component analysis, what we do in the previous session. Okay, so first I will import the pandas and numpy first. Pandas and numpy, and we'll import matplotlib c1 also. So to visualize the data, to visualize the class separation, we'll import matplotlib and cbon as well. Okay, so now what I'm going to do is I'm going to load the data set. What data set? I'm going to show you the difference between LDA and PCA with the use of iris dataset. So you can directly import from the sklearn module, dataset module. Inside we have load iris function. So this will give you the iris data, right? Load iris, and now inside the data we have the features for x, the features for x inside the data key, right? And the target variable is inside the target key. Target. Okay, so now we'll get the data set. So now you can see in the x we have 4 features, right? And in y we have 3 classes, 0, 1 and 2. And now we'll try to visualize the data set. Sorry, SNS dot, we'll put a scatter plot, and we'll give the X data. So in X actually we have four features, right? Four features you cannot visualize. So you can visualize two features, right? So let's take the first and second feature. So the X as the first feature, X of 0, and Y as the second feature, it is 1 here. And we have classes, right? So the classes are now going to separate. So we'll have a parameter called hue. Instead you can give the classes. So the classes are Y, right? Instead of the Y we have classes. So now if you run this, you will get a plot. Okay, so you can see here, now we have the plot. We have three classes, 0, 1, 2. And what is this? Okay, yes, that is a different style. Dark grid also is not showing, but anyways, so we have the three classes, and the first class and second and third class are combined. So now what I'm going to do is I'm going to apply the PCA first, okay, and then we'll visualize, and then we'll apply LDA also. So to apply the PCA, so we'll first want the class for the PCA that's inside the decomposition module. You have to import the PCA class, and you have to create the object. In order to create the object, you want to give the, before you want to give the number of components. Let's take number of components as 2. It's very useful to visualize, right? And with the two features you can visualize easily. So I'm giving number of components as 2, and we need to fit transform it, fit and transform on the data set X. Now we got the new data set with the two features, right? It's a reduced data set. Now you can visualize the data set, the same XNS dot scatter plot, and here we need to change the name X underscore new, or I think we can say PCA, X underscore PCA. Okay, so let's run this. So now you can see this data set is separated by the PCA, right? It's not considering the uh, class variables, it just is trying to separate the classes. Actually the two plots came in one single plot, that's what uh, okay. So it's just trying to reduce the data set, but it's not considering the class separation, okay. And if you try with the LDA, you will see a good class separation, okay. So to do that, uh, we have to import the LDA first from the sklearn library. uh, in the discriminant analysis. So this is the module. Inside this module we have the class for linear discriminant. put linear discriminant is a very big name, so we put an alias called LDA. Okay, and you want to create an object LDA. So the number of components the same, two components. Okay, and now we are going to fit with the data set. Let's call it as LDA XLDA and LDA dot fit transform. So here we are considering the class, right? So you have to give two values here, that is x and y both. You have to give the independent variable and the dependent variable, class variable also. So now it will try to separate with the use of the classes. Okay, now we'll run this line. You will see the same two features, but if you try to visualize it, you will see different from the PCA. So you can see here its class are separated, right? It's trying to separate the classes, but here it's not doing that. It's just converting as a linear transformation, but it is trying to separate the classes, right? So this is the difference between the PCA and LDA. Okay, I think instead of this, uh, and we can put plt dot scatter with the name of, with the labels, different labels. uh, you can give x colon. uh, so we have three classes, so y equal to 0 first, comma, the first feature 0, and for the second feature x brackets y equal to 0 comma 1. So like that you can do, but multiple classes you want to give multiple times. Sorry. Okay, now it's look like nice, right? So we'll use the same thing here. We'll copy this and paste it here. So this is the PCA here, transformation of the PCA. Now same copy and We'll paste it here. So you can see here difference between the PCA and LDA. It has the good class separability, right? So here you can see you can separate the classes. Here it's intersected with the classes. Okay, this was the LDA now, and we'll move on to the uh, next algorithm, that is kernel PCA. So kernel PC, the kernel PC is nothing but the advanced version of PCA, you can say, because why we have this kernel PCA is because in principal component analysis, it's just a linear transformation. It works when you have a linear type of data, it works well. But what about non-linear type of data? When you have non-linear type of data, the principal component analysis won't work efficiently on the non-linear type of data. On that time, we can use a method called kernel trick. We have seen before in the uh, SVM, right? Support vector machine, the kernel trick. So the same here, we have the kernel trick here. So using the kernel trick, you can transform the non-linear type of data also. Okay. So that's the written here. Principal component analysis is a tool which is used to reduce the dimension of the data. So we know that, and it allows us to reduce the dimension of the data without much loss of information. PCA is a linear method. So highlight this point, and that it is can is it okay is it can only be applied to data sets which are linearly separable, and it does an excellent job for data set which are linearly separable. Okay, but if you have a non-linear type of data set, we might get a result which may not be the optimal dimensionality reduction. And that time we use the kernel PCA, uses a kernel function to project data set into a higher dimensional feature space where it is linearly separable. Okay, it is similar to the idea of the support vector machine. That's it. Okay, and you can see the difference between the PCA. So we have a non-linear type of data here, the moons, right? So the moons here, if you apply the PCA, it won't work. So you can see the same result is coming. But if you apply the kernel PCA, you can see the separability, right? So when you have a linear, non-linear type of data, we use the kernel trick, kernel PCA. Okay, so it's a very simple algorithm is. Okay, so let me create a new file. We'll save as kernel PCA. Okay, in the kernel PC also we do the same thing, but I'm going to use a different data set using the SQL data set. I'm going to create a non-linear type of data set using some functions like make moons and make circles. So the circles also a non-linear type of data, right? Okay, so let me import that in the SQL module, data set module. We have the function make moons and make circles, which will give you a non-linear type of data. Okay, so first we'll try with the moons. Okay, so it gives two values, x and y, and you have to call this function before using it, make underscore moons, and you have to give the samples, number of samples here. Number of samples will give 1500, and I think that's it. Or you can say random state also, because every time it will give you different values. So initially we'll set a random state 0. Okay, now let's run this. You will get the data set x and y. In the in the y you will see uh, in the x we have two features, and y we have two labels 0 and 1. Okay, now let's visualize the data set. So using the scatter plot, plt dot scatter, and you want to give the first feature that's inside the x colon 0, first feature, and the second feature x colon 1. Okay, okay, we have two classes, right? So you have to give y equal to 0 for the first class. This is for first class, and we'll copy it and paste it for second class also. For second class you have to change y equal to 1, and that's it. So now you can show the plot. So you can see this is the same data as we have seen in the slides, right? So let's try to fit the PCA first. We'll see how the PCA is separating, and then we'll apply the kernel PCA. Okay, so we'll copy it from here. Okay, now to visualize this, we, we write these lines. We'll change it to x underscore PCA. So you can see this is the result of PCA. So you can see there is no change, right? There is no separability. So that's why when you have a nonlinear type of data, PCA won't work. Okay. Now let's try to apply the kernel PCA. So the kernel PCA is inside the scalar mod library. Same the decomposition module. Inside you can find the kernel PCA. Okay. And you have to create an object. Let's call it as kernel. So we'll call the class here kernel PCA, and inside the kernel PCA you have to give some parameters, right? When you have a nonlinear type of data in support automation, we have seen what type of kernel you want to use, right? So you want to select the kernel, and you have to give the gamma value. So whenever you are using the kernel, we'll have this parameter, right, gamma. And we want to give the number of components, right? Then kernel we have linear, poly, RBF, sigmoid, cosine, and the default one is linear. Okay, now we'll try with the default one, or you can use the RBF also. So let's try with the default one first, and number of components will give 2. The default one is linear kernel, so we'll try with, and then you have to fit the data set. Let's name it as KPCA data, and you want to apply the kernel trick on the data set, fit transform of x. Okay, so now we want to visualize this. Just copy and paste it here, and we'll name it as KPCA. So now you can see, wait, I think linear is not working. That's why the same result is coming. Now we'll try to use the different kernel. We'll use kernel equal to RBF. Okay. So you can see we have fitted the RBF kernel. So it's different from the previous one. So you can adjust the gamma parameter to get the better result. Gamma, let's have 10. So you can see now it's easily separable, right? So this is how the kernel PCA is working. So we have used the RBF kernel, right? RBF kernel, and we set the gamma as 10. And now it's a separable data, right? Now if I change the gamma value as 15, let's see what happens. So now it's a perfectly separable. Okay, so you can't gain this result with the use of PCA, but using the kernel trick you can achieve this. So let's try with the different one. Let's try the polynomial kernel. So actually it's not it's actually separable, but it's not like the RBF, right? It's a different. Let's try with the sigmoid. Oh, it's a very different one, right? We'll try with cosine. So now this is the cosine. It is intersecting actually. So you can see various type of kernel results. This is the result for RBF kernel and polynomial, and this one is sigmoid, and this one is cosine. So from this, RBF is the better one, right? Okay. So this is how the kernel PC is working on the nonlinear type of data. Let's try with the circles. Instead of moons, we'll try with the circles. Make underscore circle. We'll comment this line. Number of samples same, but we want to apply the we want to give two parameters, that is factor and noise. So factor we have 0.5, let's say, and the noise 0.05. Okay, so now let's run this, and we use the kernel as RBF. Okay, we'll run this whole code. So now if you see here, this one is the original data set. When you apply PCA, it's nothing changes, but if you apply the kernel, it's just simply changing, right? Okay, this is how the kernel PCA is working. So you have any doubts, we'll end up this session from here. Any doubts you have, you can ask now. Any doubts? Any doubts you can ask now. We'll end up this session from here. Okay, I hope no doubts. So we'll end up this session. Tomorrow is the end of the machine learning. So tomorrow we'll see model selection and boosting, day 29. And from day after tomorrow, we'll start with the deep learning. Okay, so this is our website, bigdatahandsome.com. So our contact number 978988844. If you have any doubts, you can message this number, or you can send email through support@bigdatahandsome.com. Our previous videos will be uploaded at the YouTube channel, bigdatahandsome.com. Okay, you can see the videos. If you subscribe to our channel, you will get all the notifications. Okay, so we'll see tomorrow. Bye.